In section 11.3, we want to look at equivalence relations. So we saw previously that the properties of reflexivity, symmetry, and transitivity are important. And we said that if you have a relation that has all three of those, that's going to be special for us. And now that's going to be called an equivalence relation. So an equivalence relation is just a relation which is reflexive, symmetric, and transitive. So it has to satisfy all three of these. So that's not. Equals is, but none of the rest of these are. So equals is our first example of an equivalence relation. So before we get too deeply into these equivalence relations, let's sort of think about what they look like using this graphical representation we've talked about. So I've just got a set here that's drawn with 4 elements, and I drew it a couple different times so that we could picture what different types of equivalence relations look like. So I want to think about equivalence relations on this set A, B, C, D, where those are the elements of my set. So I know it has to be reflexive. So each element has to be related to itself. So I'm going to go ahead and just draw in all of these arrows for reflexivity. All right, now I also know it needs to be symmetric. So here, so far, everything is just related to itself. So there's nothing to break symmetry. So I could add some extra relations. So let's leave the first one the way it is. I could say, for example, that B is related to D. But if I do that, then I also need, by symmetry, that D is related to B. So anytime I draw in an extra relation here, I have to have its sort of backwards switcheroo as well. So maybe we can throw a few of those in this example. And then maybe I'll just do a different one over here. Oops, so make sure those arrows go in different directions. Okay, so these are all reflexive and symmetric transformations now. Add in a few more to this guy. So it's reflexive and symmetric, but now we want to make sure it's transitive as well. So to make it transitive, if A goes to B, down here in the third box, and B goes to D, then I need D to go back to A, but then I still want it to be symmetric, so I'll send the one going back the other way. And here, because C goes to A, and A goes to D, I need C to go to D, but I could also go back the other way as well, so I need D to go to A. B doesn't connect to anybody, so that can kind of stay over here by itself. And there aren't any other things that are breaking my transitivity. So these are all examples of what these equivalence relations should look like. And one thing we might start to notice is when we have an equivalence relation, we basically have these islands of different elements which are connected to every other element in its island. So here I have these 4 different islands where everything is just connected to itself. Here I'm going to have an A island, a C island, because those are connected to themselves, and then a BD island, because between B and D, they're both connected to everything else in that set. So they're connected to themselves and they're connected to each other. Here I get a C island, and I get this ABD island, so it's a really big one. And then here it's pretty similar. I have that B island and then that ACD island. Or maybe I can add a couple extra relations there just to make it more interesting. And I could put in a connection between A and B, and C and B and D. But then I also need one from C to B and B to C. So basically everything is connected to everything. And that's one big island where everything is connected to everything. So we'll see when we have these equivalence relations, these islands are called equivalence classes. So they're just the set of all things that are related to everything else in their set. So the equivalence class of B is the set of all things related to B. And in fact, that's right, these relationships of reflexivity, symmetry, and transitivity are what allows us to be able to separate things out into these islands in which everything on that island is completely connected to everything else on the island. The fact that we can do that is exactly because of the rules of an equivalence relation. So that's one way we can think about equivalence relations. So again, if I have an R, which is now an equivalence relation, it's not just any old relation, but an equivalence relation, then if you have an A in the original set, then the equivalence class containing A, or the equivalence class we might here sit as of A, is the set of X and A, so that X is related to A. So all of the things that are related to A, and that's denoted as this bracket A. So let's look at an example here. So I've got this set A, which is -1, 1, 2, 3, 4. And I can think about different equivalence relations. And I've copied some from the book here just so we can really have a good set of examples. Right, so the first equivalence relation, which we saw, is this is equal to. So if I'm thinking about that is equal to equivalence relation, I'm just going to set everything paired with itself because they're all just equal to themselves. So the diagram is just going to be all those individual loops there. But we can see we get each of these individual islands here. And so when I'm thinking about the equivalence class, I'm just going to say, right, the equivalence class of -1 is just equal to the set of things that are equivalent to -1, but -1 is the only set equivalent to itself. Is the only thing equivalent to itself. So that set containing -1 is the equivalence class of -1. The equivalence class of 1 is just 1. The equivalence class of 2 is just 2. The equivalence class of 3 is just 3. And the equivalence class of 4 is just 4. Okay, so now for my second one, we want to say the relation is going to be has the same parity as. So two things are related if they have the same parity. So if they're both odd or both even. So -1 and -1, both odd. So that's in my relation. 1 and 1 are both odd. 1 and -1 are both odd. -1 and 1 are both odd. -1 and 3, 3 and -1, 1 and 3, 3 and 1. And then 3 and 3. And then separately, 2 and 2, 2 and 4, 4 and 2, and 2 and 4 are all both even. So those are also in my relation. So now everything has the same parity as itself. So I get all my little loops from reflexivity. And then if two things have the same parity, right, 2 has the same parity as 4, 4 has the same parity of 2. So we get that reflexivity. And then we can see that we have the same transitivity as well. But now if I'm looking at my islands, I get these two different islands, and that gives me these two different equivalence classes. So this is the equivalence class of -1, because it's all of the things equivalent to -1. But it's also the equivalence class of 1 and the equivalence class of 3. They're all equal to each other and equal to that set of the things equivalent to -1, which also happen to be equivalent to 1, which also happen to be equivalent to 3. And then this guy is the equivalence class of 2, but it's also the equivalence class of 4. So it's a set of all things equivalent to both of those. We could think of the relation has the same sign as. So again, -1 only has the same sign as itself. 1, 2, 3, and 4 all have the same sign as each other. So the equivalence class of -1 is just -1. The equivalence class of 1 is equal to the equivalence class of 2, is equal to the equivalence class of 3, is equal to the equivalence class of 4, and each of those is equal to 1, 2, 3, 4. If I look at the relation has the same parity and same sign as, then that's just a restriction of our same parity one. So I'm going to look at my same parity relation, but get rid of any of the things that don't have the same sign. So then -1 only has the same parity and same sign as itself. 1 and 3 are both odd and both positive, so they're in an island. And 2 and 4 are as well. So I get my equivalence class of -1. My equivalence class of 1 is equal to the equivalence class of 3, which is equal to 1, 3. and the equivalence class of 2 is equal to the equivalence class of 4, which is equal to 2, 4. So hopefully, maybe it's not going to come to a surprise as you, right? It's because we have these equivalence relations. If I have 4 equivalent to 2, then 2 is going to be equivalent to 4. If there was anything else in that set, they would be equivalent to each other as well. So basically, whenever you have two things in the same equivalence class for one of the numbers, then it's going to be in the same equivalence class for everything in there, right? So we do get these nice completely connected islands that everything lives on when we have this equivalence relation. And that's what we'll talk about more in the next section. So building off our previous discussion questions, we want to think about finding the equivalence classes for the relationship that A is equivalent to B mod 3. Because this is an equivalence class on the set of integers, I can't draw out a finite graph that represents this relation, but we can kind of use that to get us thinking about the right sort of thing. So I encourage you to think about how this might work, and we'll get to talk about that in class.